Okay, everyone. How was that filling out experience? Was it your first survey for here, anyone?
No.
Last one? Oh, jeez. I'm a little behind. They sent out the reminder last week, and I was like, oh, crap, we don't have class this week. What am I going to do? So, we got it covered. Good job. Okay, back to it. Are you ready? Okay, so we're doing post hoc analysis. So remember that this is what we do after we determine there's some significant difference in those groups to see where that significant difference between which groups it's in. This helps to minimize type 1 error, which remember is stating that the dependent variable is statistically different between the groups when there actually is no difference. And this also identifies which IV groups are statistically different. So we're going to use the Tukey test, which I know Stacy totally ruined my thunder. I called it the turkey test. So that's how you can remember it. It's after Thanksgiving, so it's the post-hoc turkey test. Okay. I'm trying to be hilarious. It's really not working, but that's okay. So it's the Tukey test, and it gives you all of these fun things that we're going to use in a minute. This is another one you can use if those assumptions aren't met, but we're not using that in this class, just for your knowledge. So when you get your results of the Tukey test, this is what it looks like. There's three things. So first we have all of these groups are over here. So this is the interaction of that first cereal brand. So that would be Cheerios with the other three. So the other three. And then this would be the second one, which is Fruit Loops with all of them. Then Cinnamon Toast Crunch, thank you, with the other three. And the last one is Rice Krispies with the other three. So what we're going to look at first in this table is this significance column. So we skip over this mean difference and standard error. What we're looking to see if there's any significant differences that are less than 0.05. So when we look down, we see that the first one is less than 0.05. So that means that there is a significant difference between brand 1 and brand 2, because that's the row that it's in, is the second cereal. So it means there's some significant difference between Cheerios and Fruit Loops, which, you know, if you think about it, that kind of makes sense. There probably would be more weight gain if you ate a crap ton of Fruit Loops instead of Cheerios. Maybe? Okay. Then the next one is also significant. So you can either look at it in this row, or I circled it down here further. Either one is fine. They're both saying the same thing. So that would be the interaction between Cheerios and Cinnamon Toast Crunch is significant. And there is no significance between Cheerios and Rice Krispies. So that means they're about the same, weight gain-wise, in our sample of rats. The second one, again, tells you that Fruit Loops and Cheerios are significantly different. Fruit Loops and Cinnamon Toast Crunch are not different because this is greater than 0.05. And Fruit Loops and Rice Krispies are not significantly different because it's greater than 0.05. And so on down the whole thing. So you just want to look to see which ones are significant. And then that's the main thing for this, is just like pulling out which ones are different. It also will give you this table with the total number and the mean and standard deviation for each group, and a little chart. Ooh, charts, yay! It also, if you really don't feel like looking at the significance, this little star thing in the table tells you which ones are significantly different. So you don't even have to do the work, but if it's easier to just remember 0.05, you just look down this sig column. Okay, so how we would write that up in a professional sentence, which you can totally copy and paste this format into your homework assignments, would be a one-way ANOVA revealed that mean weight gain was statistically different between cereal brand groups. Now here's where we pull from that first table we talked about, this first one. The F, and then in parentheses are those 2 degree of freedom values. So the top one was 3, so it goes first, and the bottom one was 16, so that comes second. And then our F value was 7.353 here, so like 316. F value of 7.353. And then we put our P value, which was 0.003. Or you can put P is less than 0.05. Either of those is fine. Since there was a significant difference, we went and looked at that post hoc Tukey test, and we then want to report which of those are different. So if we found that there was no difference up in this first part, you would just end your sentence there, because we found there was no significant difference. But since there was, we want to say that a post hoc Tukey test found that rats fed the Fruit Loops with their mean and standard deviation from that second this little table here, and Cinnamon Toast Crunch with their mean and standard deviation statistically gained more weight than those who received the cereal Cheerios with their mean and standard deviation. And then just put in here P less than 0.05, because that's what the P values were in this sig table. Does that make sense based on those SPSS output little things? Okay. So a little bit of a conclusion for this part. It's a good for situations where you have continuous variable as the DV and a categorical variable with 3 or more independent categories. If you find that that first table has the F test significant, then you use the post hoc to determine where the difference is. But if the F test is not significant, then you don't have to look at the post hoc tables. And then there's a whole bunch of these other tests. I made the output, well, I didn't make it, Dr. Metz made it, and I'm using it for these other options. We're not going to do those in this class, but if you ever need to do them in the future, you'll know how to do them in SPSS. We are going to talk about these ones just so you know what types of research situations you would use them for. So, for looking at the ANOVA and SPSS, on D2L there is that SPSS document that walks you through it, as well as the data set that was used for that, so you can practice walking through with the guide and the pictures and everything. I guess we should do that, right? Right, okay. So what we've been talking about up till this point was the one-way ANOVA. So the rest of these are not a one-way ANOVA. They're different, they have different names. We're not going to have to perform them in SPSS for this class, but you need to know when you would use them given a sample situation. Okay, so here's a brief overview of how the variables would be set up for each of these different types. So the repeated measures ANOVA would always have one continuous DV, and then there would be an IV that is either nominal or ordinally measured with 3 or more categories that are dependent on each other. So most often this is going to be time, and this is going to be the same thing as the paired t-test, except there's at least 3 categories in that IV. I have examples one by one. This is an easy way to see in an overview what the variables look like. So then the ANCOVA is one continuous DV. Then it has one nominal or ordinal IV with 2 or more independent categories. And it also has one continuous covariate. So something that we want to see, if we put that into our equation, that behind the scenes that SPSS does that make a difference on the IV we're looking at? So if we're looking at weight gain in our rats based on cereal, so weight gain is our dependent variable that's measured continuously. types of cereal are independent variable, and our confounder or covariate would be maybe the weight at the start of the study before they had the cereals. So we want to see if their original weight affected how much weight they gained depending on what cereal they had. Does that sort of make sense? So maybe the Cheerios group all weighed 20 ounces when the study started, so they only gained 1 pound eating the cereal, but the Fruit Loop group weighed 10 ounces at the start of the study and gained 7 ounces altogether. So we want to see if that starting weight affects the results we found. Does that make a little more sense? There's more examples. The factorial ANOVA has one continuous DV, and it has at least 2 IVs. One that's measured nominally or ordinally with 2 or more independent categories, and a second IV that's measured nominally or ordinally with at least 2 independent categories. So this one would be if you're measuring cereal consumption, which cereal type they had, and maybe which light source they had. So maybe we had 3 categories of light source. One had like the normal warm light bulbs. One had these light bulbs that are annoying. And then another one had no light at all. So we want to see how the light and the cereal contributes to their weight gain. A mixed design ANOVA is like almost the exact same thing as a factorial ANOVA, except the second IV, or at least one of those 3 or more IVs, has to be a time variable. So maybe we're measuring weight gain is our DV, the cereals are our IV, first IV, our second IV is assessment time. So maybe we're assessing them right after they finished eating the cereals. Then we're measuring them 2 weeks later, and then we're measuring their weight again a month later. So we're measuring time as well as weight gain as well as what cereal they ate. That would be mixed design. And then a MANOVA, exciting here, this is when you have 2 or more continuous dependent variables and 1 nominal or ordinal IV with 2 or more independent categories. Whew, that's a lot. So let's go over some examples. So the repeated measures ANOVA. You want to look to see if the DV changes over time. So if you're thinking about classes, maybe the class you're in, it's not this class, maybe you're in a paper writing type class. So you have a midterm paper, you have, that's only 2. You have a first paper draft that you have to write like 3rd week of the semester. Then you have a midterm paper that you get graded on, and then you have a final paper. So you're getting measured at your writing ability at those 3 time points. And the DV would be like grade, how your grade changes over those 3 time points. Or you could measure BMI over testing time. So if you do a health education program, maybe you test BMI before they take your program, then immediately following, 1 month after, 6 months after, and maybe another year after the program ends. So you want to see if their BMI decreases over time, or if it decreases immediately and then increases again over time. That would be an example of this. An ANCOVA is basically the same as a one-way ANOVA, but we adjust for some covariate or cofounder. So an example would be looking at post-program BMI scores if they're different by intervention group and control for the pre-program BMI score. So that was basically what I was explaining with the rats and the weight at the beginning. It's the same idea. Because if people have a higher BMI to start with, they may not see as big changes in a month, or maybe they will see big changes, but the people that started with a lower BMI will not see those big changes in that month time period. Factorial, again, one continuous DV and more than one IV, that's not time. So typically you only want to have two extra categories. You don't want to have more than that, or it gets really confusing. And there's another test that we're going to talk about next week that would do the same thing and is better for that type of situation. An example is mean post-program BMI statistically different by intervention group. So did they get the exercise group, a pamphlet, or did they get nothing because they're in a control group? And did it BMI differ by male and female? So this output table would then assess the main effect for the first IV, the intervention group, as well as the main effect for the second IV, the gender groups. And then there'd be another interaction table, like the big matrixy one that we had for one-way ANOVA, that would show the difference between males that were in the exercise group and males that were in the pamphlet group and males that were in the control group compared to females in the exercise group, females in the pamphlet group, and females in the control group. It gets really big and really confusing, and that's why we're not going to do it in this class. But if you get a scenario that says, is the mean post-program BMI statistically different by intervention group with those 3 categories and gender with those 2 categories, you would know that it's a factorial ANOVA, I hope. Mixed design, again, same thing, just one of the IVs is time. So does mean BMI statistically differ by intervention group and over time? So pre, post, and 1 year after your intervention. And again, it'll produce all of those effect tables. The effect for just intervention group, the effect for just time, and then the effect of both on BMI. The ANOVA assess multiple continuously measured DVs, so 2 DVs or more on one categorical IV with independent groups. So this helps to control type 1 error because you minimize that multiple comparison. Instead of doing multiple independent t-tests, it minimizes that by doing it all in one test. So an example are multiple continuously measured lab results statistically different between patients with and without cancer. So maybe we have lab results across a person's entire lifetime. So if you go once every year, you're going to have a lot of lab results. And maybe it's just cholesterol that you're measuring. So your cholesterol levels over time. And you're looking to see if you have cancer, how those lab values differ than if you don't have cancer. Does that make sense? Sort of. Woohoo! That's all for the slides. Yay! Oh, the other thing I wanted to show you fairly quickly that may be helpful moving forward is this statistics matrix that I have in Module 7. So this, I know when I first showed it, you were all like, ah! But if you think about it, we've learned a few of these now. So we've learned this Z or T test with one sample. So those were those annoying ones that you had to pull out the Z and T tables and look up the numbers and do all that. The binomial we didn't really do. Then we did the independent t-test, where the DV is continuous, and the two samples or 2 categories of the IV are independent, or use a paired t-test if the 2 categories are paired, so 2 time points. We've also done the chi-square, which is this x squared. If you have a nominal DV, with 2 samples or 2 categories of your IV, would be all of these are chi-squares, except if you get above 3 samples in your IV, it would be a Cochrane's Q, but we didn't talk about that, so don't worry about it. And then if your DV is ordinal, but your samples are independent, then you would use a chi-square. We didn't talk about this one. So basically, you would use a chi-square. We've talked about independent t-tests and paired t-tests. Now, if your DV is continuous and you have 3 or more categories that are independent, you would use a one-way ANOVA, which we just talked about. If your DV is continuous, you have 3 or more categories and they're paired or dependent on one another, aka 3 time points, you would use a repeated measures ANOVA. Then if you have a continuous DV, and then these other ones describe the IVs that are associated with the factorial, mixed design, and we didn't get there yet, and mixed design ANOVAs. So you may have examples of those 4 types of ANOVAs on future homeworks. I don't think I put any on this one, but you may see them. So this may help you. There was also a list of websites that are more click-through and interactive on this Module 7 page. So here, there were a list of a bunch of different ones, the table and flowcharts or the interactive ones. If those are more helpful to you, that works too. But this way, it's a little easier to go through that decision-making process after you determine what the IV and the DV are in your example. Let's see. Any questions before I go over the homework for next week? All right, so here's your homework. Part 1 is like one example with a couple of little mini questions. So I'm not going to read this for you, but you're going to enter the data into SPSS. Remember, 3 categories. You have to label the categories as your IV and these values in the table as your DV. Remember when we talked about the categories and the moving with the age and the BMI? Okay. So that's what you need to do for this part. So you're going to identify the DV and IV. Be sure to include their level of measurement, nominal, ordinal, or continuous. And if they're nominal or ordinal, put the categories. So the screenshot of your data view in SPSS, I just need the data view. I don't need the variable view. Unless you want to give it to me, that's fine. And then you'll do the appropriate test, one-way ANOVA, and report your results here. So you can use those formats on that Word document or on the PowerPoint and just fill in the different names of things and the different values of things, if that makes more sense to you. Or you can write it your own way. As long as you include everything appropriately, you'll be fine. And then this fourth question is asking you to think about the results in terms of practicality or feasibility of implementing different programs. So the example is just kind of saying that there's these 3 programs that the agency could use. Based on your statistical results, what's the best option? And based on those results and maintaining the smallest budget possible so you can save money, which one would you choose? And then the second part is answering some questions from this OPD 2005 data file on it online. So I already did the codebook table for you, so these are all labeled appropriately. So part of the rest of this should be pretty easy because you just can look here for what type of variable it is. What you're going to have to do is choose between these 4 tests that we've learned so far based on your DV and IV, and then actually calculate go through SPSS with this data and find the result. So there's 4 of them. I had more, but then I was like, you're going to kill me, so I took some off. So you have to identify the DV, the scale or level of measurement, cough, cough right here. Pretty easy. You should all get those right. Which test you should use, and then your write-up of the results of that test. If you want to include your SPSS output here in addition to your write-up, that is fine. You don't get bonus points for that, but if you want me to see it, go for it. If you don't, it's okay. And the same for the rest of these. Then I just have a note here that the total points available on this assignment are 35. It'll be graded as if there's 30 points, so there's like a bonus 5 points kind of in there. So if you get less than 5 points wrong, you'll have a score above 30. If you get more than 5 points wrong, you'll still have a score below 30, but it might not be as below 30 as if there were only 30 points on here. Does that make sense? That's kind of what I did on the last homework too. And then just describing how you felt when you did this assignment, or any thoughts you have that you want to tell me, or anything really that you want to say. It's fine. But remember, I do read this before the end of the semester. Not that that will affect your grade, but just don't be too crazy here, okay? Any other questions? Okay, I will see you next week, and we will talk about correlation and logistic regression, and my SPSS will work.